Okay, I hope you had a good weekend. There was a new announcement, which maybe you heard come out, I think just yesterday, that our closure is going to continue until May 31st, and then they're going to reevaluate again after that. What that means then is we have at least another month of communicating and learning this way. So, one of the things I started this morning, which is why this video is posted a little bit later than usual, is creating the YouTube channel that I will be using to share videos so that the compression happens and will allow you to use up less data as we continue to go forward with this. So my plan is to try to put stuff on YouTube today and backload all the videos and then make sure when I share from now on that it'll go to that. Okay. So that is new information in a new way I'm gonna attempt to share. What I would like to do this morning is to revisit some of the topics from last week. One of the things we talked about last week was human vision and then how you can correct different vision problems. One of the things we talked about was laser eye surgery, and I attached a clip which had no commentary, unfortunately, and you just watched sort of what happened. There is a textbook page that I'm going to add to this lesson, which you can read if you don't have the textbook at home. It's page 480, I think, which will describe what you saw in a little bit more detail. It makes it a little bit clearer. It's usually the cornea. It's always the cornea, I should say, that they are working on. There's just different ways they can do that to main types of surgery they used, at least in the past. I haven't looked at anything super recent and I haven't had it, so I don't know the most up-to-date surgical procedure they're using to do that. But really what they're normally doing is reshaping the cornea, which would be, let's just do this for a second, this front part right here where my cursor is, okay, and not the lens behind. They both have that outer bend to them. They're both transparent. So the light actually bends a bit twice, even though we don't talk about it too much, when it hits the cornea and again when it hits the lens. But we in our modeling really just show it, for the most part, bending when it hits the lens. So what I wanted to bring this page up again for, is to talk about what happens with glasses. Which was another topic of last week. Right now we have normal vision on this person, and so they can focus for both near and far, and they can see objects both near and far. If I switch to somebody who is nearsighted, what that means is that they can see, as we talked about last week, what is directly in front of them, but not what is far away. So they can focus on what is close, but they cannot focus on what is far away. So the glasses they wear help them focus on those distant objects. I'm using this one again because of the ray diagrams. So this is a converging lens you have in the eye. It means the light rays are going to come into the focal point. And so in this particular modeling, it shows you where the images are landing, where they all come together. Okay. So we did some drawing right at the end of last week to show that as light rays come through these lenses, they go through a focal point and then you create the image somewhere in relation to that focal point. This one is a little bit different. So how this is showing it is the image is landing where all these light rays converge. Right. So right now for this person, I've got an object nearby and their focus is near. So where that image is going to show up is right on the retina where we want it to be. Okay. This is a normal vision person, sorry. If I switch the object to far away, and I switch the focus to far away to match it, their lens got thinner, stretched out, and allowed the image to still fall where it should on the retina. Okay, let's switch it to somebody who is nearsighted. Okay, so no problem when the object is close by and the eye is trying to focus on that nearby object. I change it to put the object far away, and their eye attempts to focus on that distant, far away object. What happens is this point where the light rays are converging is where the image is, and it's in front of the retina in this case. So it looks blurry back here. If the retina was right here, it would look sharp and crisp. But because it focused in too soon, the image is actually in focus right here. It looks blurry. So how we correct for that is to put a lens in front of the eye, glasses or contact. I'm going to correct for that. In this case, use a diverging lens. So the idea is it moves the light rays a distant or apart, and then when they hit the converging, they start to bend together again. But because I already sent them out a little bit further before they got here, the image appears directly on the retina. Okay. If we switch to a far-sighted individual, so the object I'm going to keep far, focus far, they can see distant objects no problem. Okay. Far. Okay, just object is far, focus is far. They can have their lens extend like that so that the image is falling on the retina. The problem for a far-sighted person is with objects right in front of you. So if I bring the object near and then I try to focus on that near object, the lens did bulge more in the middle, but not quite enough. You can see here that it hasn't come to a point. So the image isn't landing on the retina. The image is actually landing back here. So to correct for this, we use a different kind of eyeglass. We use an additional converging lens. So it'll bring the light rays in more before it gets to this one. And so it lines it up with an image landing on the retina. Okay. Now, if you need bifocals, that means you can't focus on either. So if I have bifocals, I have a near object, trying to focus on it, not getting to the right point, I can correct for that by using this part of my eyeglasses, the part that's the converging part. So when I look through the lower part, it helps bend the light rays in. You can see they were going out, bend it in, hit my own converging lens in my eye, bends it more. The image falls exactly where it should on the retina. Now, if I move the object far away, you can see how these eyeglasses have two different shapes to them. Move the object far, focus on far. The image is landing before the retina, so I'm going to use the same eyeglasses, but look through the upper part. The upper part is a diverging lens. So as the light rays come in, it causes them to spread out a bit more so that when they do come together, the image will fall on the retina. Okay, so I'm using this website again to demonstrate to you how eyeglasses can correct for these light rays that are coming in that your own converging lens just can't accommodate depending on its situation. Okay, where I want to go to next was, you will see attached to this video a couple of our own videos my son and I made to show you how a converging lens focuses down to this point here. And we played around with some leaves outside this morning since it's such a bright and sunny day. Another simulation which I wanted to show you, I'm going to flip over to this and fill this up. This is where we left off on Friday. So we had drawn our own image, our own ray diagram image. We had a converging lens. And then I talked to you about this being called the principal axis here. I talked to you about the middle of the lens being the axis of symmetry, and right in the center of both vertical and horizontal is the optical center of that lens. I talked about how you have a focal point on either side because light can come through this way or this way. And so if I shine a light over here, those light rays will focus and pass through this place. If I shine a light right here, it will come through and pass through this side. 2f is just exactly doubling this distance. So if f, what is it here? F is 20 centimeters. Focal length is 20 centimeters. That means from the optical center to F is 20 centimeters on both sides. That means this just means 40 centimeters out. Okay, so we have 3 rays here. I'm just going to turn these off for a second. This is my object, and this is my image. So we drew this as an arrow the other day, and I feel like I had my arrow something like this. Like it was almost twice the distance from F, but not quite. And the first light ray I showed you, I said if you come out, and you always come out off the top, if you head out parallel to the principal axis, when you hit the middle, that light ray is going to be refracted, which means it's going to change direction, continue in a straight path, but headed towards F and then continuing on. Okay. Another option is to use a light ray that instead of starting out parallel, goes through F right off the bat. So heads in this way. When it hits the lens, this time it's going to be refracted so that it travels out parallel to the principal axis on the other side. And then the third ray I said is if you travel through the optical center, it'll just keep going straight. So you need two lines to find your image. You couldn't really find it with one, it's just filling it in there. So for example, if I did this one and this one, where they cross right here is where my image is. If this were the eye, then that's where the retina would be. Okay, you want it to fall on the retina. I could, instead of using those two, use these two, I get the same place. Those two, I get the same place. All three, same place. Okay. Now, what we noticed the other day was that when we had it in this position, this was upside down. Okay. You can actually measure all these things. So the object, this is how far it is from the optical center. This is its height. This is the image distance, and this is its height. So this one is actually farther from the middle of the glass than the original object. It is a little bit bigger. It's 11.4 centimeters. And this negative just means it's upside down. Okay, all this is going to be kind of new learning about how you describe an image. So what I wanted to show you with this is that I can move my object and it will change aspects to the image. So we're not changing the lens. It's not like your eye. Your lens can actually move a little bit. We're not going to change the lens at all. We're going to move where the object is and see what it does to the image. So the reason the lens moves in your eye is so that the image will always fall on the retina, right? So if I move this back here, going farther and farther from the lens, you'll see the object is staying upside down, but it's getting smaller. And I could actually measure if I wanted, right? So the farther back I go, smaller it goes, come towards, goes farther away from the lens, gets larger and larger and larger and larger and larger. Okay. Now, if it goes and actually stands on F, some funky things are going to happen. It's going to happen because this light ray is going to go up, down. So I'm just going to move it here. Usually we would draw these all in class, but I'm going to move it here, right on top of F. It says the image is out here, but actually you're never going to get to the image. So what has happened is, which one do I turn off? I don't need to use that one because it just goes up, down now. Can't go through it. Is these two lines, when they come out on the other side of the lens, are running parallel to each other. So they're never going to find a place where they cross. So you're never going to be able to get an image. So if you had a lens like this and you put something right on the focal point of that lens, you won't make an image. Okay. You will never be able to see what you want on the other side. So on the one side of F, we always get an image. Just the closer to F, the farther away it is. Farther away from F, the smaller it is, and you can see, okay, closer to the lens, smaller. As I come back again, farther from the lens, bigger, but all its other properties are kind of staying the same. All right. I'm going to come back to that different day. If I go to F then, we've talked about how there is no image ever. If we go on the inside between F and the glass, the image is going to show up behind the object. So what you have to do for this one is, once again, we can't use this through F1. I can use the ray that goes towards the glass, turns to go through F, and then I can use the one that goes through the optical center that just keeps going straight. You can see that these are actually traveling apart from each other. They will never cross over here. You will never get an image on the other side of the lens. What is happening is the image is showing up behind here. So I follow these lines backwards to find where they cross, and that is where the image is. So this one looks really different. It's larger than the object. It's upright. It's in the same position. But I could never find this on a screen. I could never capture this anywhere. So this is sort of how like a magnifying glass works. It takes what's in front of you and it makes it bigger. So, but you can't actually put a paper anywhere and catch what you're seeing through the magnifying glass on anything. So we call this a virtual image. Whenever it is behind the object like this, it is a virtual image. Here's a little thing to help you put that together. Virtual are always upright. Okay, so if it's upside down, like over here, it's real. I could put a screen here and I would be able to capture this on a screen. So actually, here's what I was going to say, which I said I was doing for another day. I'll just repeat it today and another day. Is that in a movie projector, when they use the film, the actual old school film, and they put it in the projector and show you in the movie theater, that goes in upside down. And the reason the film goes in upside down is because it comes through the projector's lens, which is this, and then it travels and it hits the screen right here. And if it was film was loaded upright, the movie would be upside down. So if you load the film upside down, the movie appears upright on the screen. Okay, so this would be an example of where you can actually capture the image on a screen, real upside down. If I come close to the lens, I will create this weird virtual image that is larger than the object, like you see with a magnifying glass, where you can't actually capture that anywhere. And when it is virtual, it is upright. All right, so I will give you a link to this as well, so you can play around in here. We're just going to stay with converging today, and then on Wednesday I'll do diverging, but you can go to town if you want, and go ahead if you want and look and see what's happening. To avoid keeping this video too long, I'm going to go to our note now, and we're just going to take a quick note on what it means to describe an image as real, virtual, upright, inverted, all those different pieces. Okay, so let me get out of here and let me go over here. Okay, and here we go. You can add this to the note you started the other day if you like. So I'm just gonna actually start new. Okay, we're gonna call this image properties. Okay, so the first thing that you can describe about an image, I'll do number one, is its size. Okay, and this is relative to the object, which just means compared to the object, okay, compared to the first thing you put in front of the lens. So usually we say that it's things like it is larger, smaller, it could be the same size. Okay. The second thing you can describe about an image is what we call its attitude. It has nothing to do with its sassiness. Attitude. Okay. This is sort of its position compared to the object. And the two terms we use would be upright or inverted. Okay, so if the object, for example, if we use our arrow, is like this, upright would mean the image is also like this. If the object looked like this, inverted would mean the object is upside down. Okay, so this would be the object, and these would be your image options. Okay, either upright or inverted. The third thing that we talk about is the location of the image. Okay, and so we describe this relative to the lens and wherever F is, where the focal point is. So I could say something like the image is between the lens and F. Okay, I might say something like opposite side of lens, etc. You're just basically telling them where it is. You could put a numerical value on this if we were doing experiments in class. We can actually measure, like it shows in that simulation, how many centimeters from the optical center and things like that. You can also measure the size. So in class and like in that simulation, they don't just say it's larger, they actually say how many centimeters it would be. All right, the last one is the weirdest one to me. This is the type of image. And there's two words to choose from. There's real or virtual. And this is what I was trying to describe with the screen. So a real image, this little thing here, captures, is what can be captured on a screen. So the back of your eye would be the screen, an actual screen like in a movie theater, film in a camera, which we'll look at, things like this, where you can take the image and actually physically see it show up on another surface. Virtual cannot be captured. Not really helpful. It's kind of the opposite of this. Cannot be captured on the screen. It's appearing somewhere between the lens and the past the object in this weird virtual world, like what you see through the magnifying glass and those enlarged letters or numbers that you can actually capture anywhere, if that makes sense. I don't feel I ever do a good job of describing this, but if you can understand this, this would be the opposite. The little trick that goes together to help you kind of make sure you're doing your drawings right, possibly, is that if something is real with the converging lens, it will be upside down. If something is virtual, it will be right side up. And if we were in class and we could actually hold up these little lenses, you could move them from your eye and actually see when it flips from being upright to inverted. So we could take these little lenses and we could change how far it is from the eye, and at a certain point it flips and goes upside down, and then you bring it closer and closer and closer, and it can and flip and go right side up. So that would be fun to do, but you just have to trust me on that. That with the right lens and playing around with the right thing, you can actually see it go from one to the other in a converging lens. So what I'm going to leave you with for now is an attempt for sort of your work afterwards to do some ray diagrams. So normally in class, I would give you time to try and play with this stuff and work on worksheets that are related to this stuff. So for example, one that we can draw together, and I'll do it right on here, is, let's say we have our principal axis, okay, and we put our converging lens on here. Okay, there's the center of it there. And I make the focal point, I'll do the hard one, make the focal point here. Should have a ruler, less than perfect times, people. Okay, I hope that's the same distance. Now I'm going to do this situation where I put the object in front of F because I know it's going to make the virtual image I want to show you. So let's say I do right here. I need two rays to find where the image is. I can't use the go through F because F is behind me here. It's not going to take me to the glass. So I'm going to use the only two rays I have left. Oh, actually, that's not quite true. I could use the F on the other side, but let's just keep life simple here, people. All right, I'm going to do a parallel one till I hit the glass. Arrow to show where it's traveling. This is the one that if I start by parallel, when it refracts through F. Okay, and I let it keep going because I don't know where that image is going to be. And the other one I'm going to choose because of the situation is to go through the optical center and then keep going straight. Let's try that again. Terrible. Unacceptable. Okay, start from the top, same place. Try to hit the center. Oh boy. So much better. Okay, so what I can see here is that these two are never going to meet. So the image is not going to be on the other side of the lens. It's going to be back here in this virtual world, back behind where I started from. So how to find it is to do this backwards tracing. So I'm going to take this ray that is headed in that direction. Oh, sorry, my arm's kind of in the way. And I'm going to, oh boy, come back like this. And I'm going to take, see that? See what I did there? And then I'll take the other ray, which I realize is never going to meet to find an image on that side. And I'm going to trace straight back from it. Oh, I should have lined it better there. Okay, I keep them dashed to show they're not actual light rays. The original light rays went this way and I traced behind. And then I see they crossed right here. So that's where the top of my image arrow is. And I would draw with a ruler, breaking the rules, down to there. And I would have to label these because it's kind of hard to tell what's what. Ugh. This is a terrible idea. Okay, this was the object, too many arrows. And this is the image. Okay, so then when I go to describe it, we call it SALT to try and remember the 4 properties. SALT are the 4 things I want to say about this image. SALT, or the S in SALT stands for size. So I could say it's larger than the original object. I could, if we were being quantitative, actually measure it to see what its size is. Attitude is whether it's upright or inverted. So in this case, it is upright. The L in SALT stands for location. This is on the same side of the lens as the object behind F. So I'm going to write behind F bracket same side of lens. Behind F, same side of lens. And the T in SALT is type. And because it is on the same side as the object and I had to use these dash backwards lines to find it, this one is virtual. Okay, so that would be what you do. You try all the different situations. You draw the principal axis, you draw the converging lens, you put in your F, and then you play around with what if I put the image, or what if I put the object here, and then you draw to find the image, describe it. What if I do where I did it here? I put it in front of F. Draw the lines, find the image, describe it using SALT. What if I put it right on F? That's the one where you can't find an image. So then over here, you just write no image and you just keep moving it around on the principal axis to see where it shows up. Okay, so that's what I want you to try for yourself with the time you have. And then probably Wednesday, maybe a good day for another little Google quiz check on to see how you're doing with the converging lens. Talk about in a little bit more detail things like cameras, movie projectors, and things like that, and then switch to diverging lens. So I know that was a long one because of all those pieces. I'll see how my YouTube stuff turns out. All right, and I will be talking to you guys later. So yeah, this is where it always falls apart. Okay, bye everybody.